Okay, problem number 2 here on 2023 AB. We've got Steven swimming back and forth on a straight path in a 50-meter long pool for 90 seconds. And velocity is given to us by this messy function here, which I have already gone ahead and put into my calculator right here and defined that as v of t. Okay, so where was I here? Got it? T is measured in seconds. V of t is measured in meters per second. Okay. So for part A, we're supposed to find all the times t on the interval from 0 to 90 at which Steven changes direction. So the first step to that is we're going to have to take our velocity function and set that equal to 0. But remember, guys, the quick thing about this is just because velocity is equal to 0 doesn't necessarily guarantee that we had a change in direction there. Velocity actually has to change sign on that interval. So for that reason, it might be faster to go ahead and graph this function and then just take a look at where from 0 to 90 it crosses the x-axis. And I think I can get all that across. Having defined the function already, I'm going to add a graph page right here. And for f1 of x, that function was defined as v of t in my calculator. So I'm going to hit, all right, let me get rid of that. Okay, gotcha. No, I wanted this. Okay, v, and when we're graphing on the Inspire, we've got a graph in terms of x here. So we'll hit that, and that didn't tell me very much, but I think I better change my window around here. So I'm going to go to Window, Entry, and Window Settings, and we were on an interval here from 0 up to 90. So I'll put 0 in for, no, 0, there we go, for our x minimum, and we'll put 90 in there for our x maximum. Not worried too much about scale. And for y min and y max, as long as it goes from negative to positive, we're going to be fine there. Okay, now this was not the tricky one that I thought that it was going to be here, everybody. I thought there might be some spots right here where this thing bounced off the x-axis, but it looks like this velocity function is only equal to 0 at t equals 0, and again, I don't know, maybe 2/3 of the way along from 0 to 90, maybe somewhere around 60. So let's find where that point is. I'm going to go to Analyze Graph and try to find a 0 to this function, my lower bound being roughly there, my upper bound being there. Oh, turns out it was actually at 56, which now that I think about it, I probably should have known because of the 56 right there. Yeah, and sine of pi is going to equal 0. Yep, my mistake. All right, anywho, where are we there? So v of t is equal to 0 at t equals 0 and again at t equals 56. But it only changes direction at 56. You can't change direction at the moment that you start there, guys. So we could say right here that Steven changes direction only at t equals 56, and the reason why would be because v of t changes sign at that time. And if we wanted to be specific, we could say that velocity changed sign from positive to negative there, but that's really not necessary. Even if it changed from negative to positive, that would still justify a change in his direction. So, looks like that's all we had to do then for part A. All right, for part B, supposed to find Steven's acceleration at t equals 60. So remember, this is the velocity function, and acceleration, let's jot this one down, a of t is equal to the derivative of velocity. Now, a lot of you probably knew that without writing that down, but I'm always trying to communicate to the AP grader that I understand where the acceleration function came from. So what we really need to do now to find acceleration at 60, that means we're going to go to the calculator and type in v prime of 60. I wouldn't be surprised if a lot of people here got the right answer for part B, but didn't get full credit, maybe because they didn't explain this concept. You don't know anything about the acceleration function, so you've got to represent it in terms of velocity. So, just like we did in problem number 1 a moment ago, I'm going to go back to my calculator page, and I'm going to do, let's see, we're going to go to our calculus menu and do derivative at a point. So our variable here, yet again, is, let's go back here, and our variable is t. We're evaluating this at, I believe it was 60. Let me double check that. Yeah, v prime of 60 is what we're looking for. We want the first derivative, okay, of our velocity function. So here we go, v of t. Gotcha. Doing all that with respect to It was time right there. Okay, and as a decimal then, I bet it would have given me that anyhow. Looks like we got this value here of negative 0.036. So negative 0.036 looks like our answer to the first part. Show the setup for your calculations, that's it right there, and indicate units of measure. Now, since velocity we said was measured in meters per second, the derivative of that is going to be meters per second and then per second. A lot of people prefer to write that as meter per second squared, and that's fine. They'd give you full credit for that unit as well. Okay, now the next question is Stephen speeding up or slowing down at a time of 60. And I'll bet a lot of people looked at this right away and said that he's slowing down because his acceleration is negative. But when they ask this question about speed, not velocity, increasing or decreasing, you have to compare that then, everybody, to Stephen's velocity at that same moment, which wasn't given to us, but we can get that pretty quickly from the calculator here just by typing in, all right, here we go, V of 60. Let's do that. Okay, got it. And yeah, let's see what we get for that answer right there. Negative 0.160. Okay, negative 0.160. And that one would be in meters per second. They didn't ask for it, but here's what we needed to know, guys. Velocity is negative at this point. So what this means is we have a pool, which is probably rectangular, and that at this moment here, guys, it's 60 seconds. Well, this kind of pans out. We already knew that velocity was greater than 0 for the interval here from 0 to 56. What that tells me is that for 56 seconds, Stephen swam from left to right, and his velocity there was positive. But then after 56, he turned around and started swimming backwards. And so for this interval right here, his velocity was negative because Stephen was swimming to the left. That's what I see right here. And since his velocity is negative and his acceleration has the same sign, they're working together now, that means that Stephen is actually speeding up. So our answer here for the second part of B is that, let's get this right here. We'll try to do full sentences right here. So Stephen is speeding up at t equals 60. And the reason for that would be because velocity at 60 and acceleration of 60 have the same sign. Now that might be true at other times here. For example, on that part to the right here when he was moving, there are probably times when both his velocity and acceleration were positive. But I would think that as Stephen was getting close to the wall right here, I'm just guessing here what I know about swimming, which isn't much, that at that moment right there, his velocity was positive, but his acceleration was probably negative, moving in the other direction. And when velocity and acceleration work against each other, an object is slowing down. But there's our answer for part B. Okay, C, find the distance between Stephen's position at t equals 20 and his position at t equals 80. Now, I think this is going to be interesting, guys, because at 56 seconds, that's where all of a sudden he hit the wall and moved backwards. I'm just kind of curious. The answer to this could actually be 0. There could be no distance between them at all because he passed this, some magical threshold on the way from left to right at 20. He might hit the same point on the way back. Regardless, though, I'm thinking too far ahead. We're just trying to find a displacement, the difference between or distance between two positions, guys. So that's what we're looking for. And the formula for delta S, displacement here, is simply the integral here. This is going to be from 20 to 80 of his velocity function, which was called v of t, was it not? It was. So from 20 to 80, this is going to give us the change in position here for Stephen's position here from 20 to 80. So I showed them what it is I'm about to put in my calculator. Now let's go ahead and do it. So calculus menu, we're going to do an integral from 20 up to 80, gotcha. And then our integrand, all right, still kind of a pain to get to here, guys, is going to be v of t, gotcha, all of which is being taken with respect to t. Okay, gotcha. And when we hit enter, all right, we get 23 point, that's going to be 384. Let's write that down, okay? So 23.384. 0.84. Let me make sure I got that right before I move on. Yep, got it. And now, okay, now show the setup for your calculations. Okay, that's it. Now, they didn't ask me here. I thought they were going to. What that actually tells us here, guys, is that in terms of the rectangular pool right here, his position at 80 is actually 23 whatever meters greater than it was at 20. So maybe somewhere around here at t equals 20, Stephen was traveling from left to right. Then he made the switch and he's moving back over here this direction, and this is where he ended up now. Nope, sorry, that was back to what I was thinking before. He didn't get back to that same spot right over there. He's actually further right, so maybe something like this. Okay, and the distance now, this is where he is at t equals 80. Let's ignore that. And it's this distance between these positions right here. That was 23.384 meters. But like I said, they weren't asking for that. Okay, that's part C. On to D. Find the total distance that Stephen swims on the interval from 0 to 90. Hopefully you guys recognize that. Total distance traveled is a formula that we've used throughout the course of the year. And it's difficult on a non-calculator question, but on calculator it's pretty simple. It's really just the formula for displacement from 0 to 90 of your velocity function, except for total distance traveled, we do an absolute value around that velocity function. We don't want to take into account the idea that he's moving backwards when velocity is negative. So if we simply type it into the calculator like this, I think we're going to get our answer right away. So here we go. An integral now. This interval is from 0 on up to 90. Gotcha. And we need the absolute value of that v of t function. Now remember, you can always just type in ABS. I've got a key for it right here. So there you go. And then we're doing v of t, all right, all of which is taken with respect to t, and this should be our answer here, 62.164. 62.164. It didn't ask for units, but everything would be in meters right here and show the setup for your calculations. Okay, and that is where we are at, 62.164. I'm kind of curious then, whoa, how that relates to what we knew here overall. Yeah, he's on a 50-meter long pool. Gotcha. So again, back to this same diagram over and over and over again. We know that he swam 50 meters. Okay, going all the way down there. And we know that that took him 56 seconds to do that. And then he turned back around, and it looks like from 50 meters to 62, looks like he only made it about another 12.164 meters coming back. And then that took him an additional 34 seconds. So it looks like he was definitely moving faster on the first leg of this than he was at the end. But I suppose that's realistic for a swimmer as well, as you start to get a little bit tired moving through all that. Okay, guys, that is where we're at this point, and that takes care of everything then for problem number 2.